Welcome to the Moldex3D Advanced Tips and Tricks. My name is Alex Baker, and today we'll be going over hot runner setup and shear heating through runner systems. Some subtopics you can look forward to are importing a hot runner system, discussing the difference between line-defined and solid geometry in Moldex3D as far as the runners are concerned, explaining the importance of geometric and rheological balance through the runner system, and visualization of the shear heating in a hot runner system after the simulation has been run. We're talking about the runner system. We're really talking about the volume that it takes to go from our nozzle at our barrel or at our machine all the way down to the part geometry. So there's a couple of ways that you can bring in runners into Moldex3D, or really consider runners into Moldex3D. And I mentioned both of them earlier, the first of which is a line-defined runner, just like we did with the gates. You can do a line-defined runner, and it'll create a very high-quality mesh. It's very accurate, and the computation time that we get from it is actually much lower than the second type of import, which is a geometry-type runner. So we do have the flexibility to import a CAD geometry runner. However, we will be creating a boundary layer mesh, which obviously boundary layer mesh is a good quality mesh. Just not as good as the hexahedral type mesh that we create most of the time for our line-defined objects. So we're going to go through a little bit of a practice, or I guess a tutorial on how to draw lines in Moldex3D. I know it can be a little complicated sometimes, so I want to make sure that everybody has the understanding of creating lines in Moldex3D and how to actually go about doing that. So what we're going to do is import geometry, just like we did for the part insert. We're going to take the third step file here, which is called Shear Imbalance. And this is just going to be an 8-cavity mold, nothing too complicated with the parts themselves, but you'll actually see a bunch of dots, and these dots are really just the outline that I've made for the runner system. This will just give us a bunch of reference points, just make things a little bit easier. You can feel free to freeform your runner system if you want to, but this is just to make it a little bit easier for everybody. And I'm just going to select all 8 of my parts. To multi-select, you can either box select. In this case, box selecting is going to be a little bit tricky just because you're going to grab the points. So I would recommend using the Shift left click. This will allow you to append your selection. And then I'm going to attribute these. Now, being that I have multiple objects attributed, you'll note that the double click method does not work. If I double click, I'll only be selecting one object. So I will want to make sure to use the right click method. Right click, edit injection molding attribute, and that will allow me to assign all 8 of these at the same time. So I'll assign these as a part. And that's really it as far as the attribution goes for now. We're just making sure that we have a part geometry in our interface. It is actually important for the next step that we're going to be doing. Now you'll actually note that the step file that we imported here is able to hold these dots, and step files are also able to hold lines as well. So actually, I see a lot of users importing the lines along with the geometries, and that is perfectly okay. You can do that. The lines, as far as Moldex3D is concerned, if there's lines that don't do anything, that is actually not a problem because Moldex3D only considers objects that have been attributed. So if for example, when we're done with all these dots aren't attributed as anything, and therefore Moldex3D doesn't care about them. We're just using them for reference points, and the same would go with lines. If you have reference lines, then those lines wouldn't be considered in the simulation. They wouldn't impact the simulation at all. However, once I make my runner system using these points, or even if I were to import my runner system as a series of lines, then after I assign those, they will certainly be considered in the simulation. All right, so let's move on to actually creating our runner system. So like I mentioned, there's 2 ways that we can bring runner systems into Moldex3D, or really consider runners in Moldex3D, and that's by either importing the CAD geometry or creating a series of lines and then assigning the volumes based on the line attributions. In this case, we are going to be using a series of lines. and we can do that pretty easily, I'll say, especially if you have these sorts of reference points. You don't necessarily have to import the entire runner system. If you just have a series of reference points, that's usually good enough to create your runner system as we're about to do. So this is pretty much just a connect the dots exercise, and you can really create your runner system however you want. I've just given you a reference if you want to keep things nice and simple just from a learning perspective, but feel free to ignore these dots if you want to create a more complicated runner system or get a little bit more practice. So the way that we're going to go about creating our runner system is through the Tool tab. The Tool tab has a bunch of different functions, but the main one we're going to be using here is the line function. I usually start from my geometry and then go all the way out to my sprue. It's very easy to start at the sprue and then go to your CAD geometry, or it's easy to think that that's the best way to do it. And ultimately, you'll find that that is pretty difficult just because there's certain connections and certain orientations that are going to be connection point dependent. So if we start from the bottom of our system and work upwards, usually we have the connection points in order to actually create our entire system successfully. So what I'm going to do here is, I currently have my snaps deactivated. The snaps are going to be extremely important here. So I'm going to turn on my snaps down at the bottom right corner of my screen. I'm going to use this checkbox to turn on my snaps. And because I have a bunch of point objects, I'm going to use the first snap here, which is called the point snap. All right? And drawing lines, just like in any software, we're going to start from one point and go to the next point. So I'm going to go from here to here. And now this would be extremely tedious to have to go and click the line function every time. And this is actually, we used to have to do that, and it was a big pain in the ass. So we actually have a shortcut. If you press the space bar allows you to repeat the last command that you did. So I'm going to go from the top of my gate in this case. This is just going to be the top of my gate ultimately. And I'm going to go to the top of my runner, or the top of my drop in this case. And I could repeat that for all 8 of these drops if I wanted to. A shortcut here, I can highlight the curves, right click, copy selected. So I can actually just copy these 2 lines from the bottom of this drop or even the top of this drop. Any reference point will work. I can copy these objects from one point to the next cavity here. Now we have this option here called consecutive copy. Consecutive copy allows me to just do this copy multiple times. So rather than just doing one and then having to go back into the function and then doing the second one, it just allows me to kind of rapid fire them. And then I'll be able to just kind of go down the line and create all of my systems here. So as long as you have a congruent system across your, or I guess a congruent drop system for all of your cavities, you can use this copy type approach. All right, now that we have our drops, I'm not going to assign anything yet. I usually wait to assign everything until I've created my entire system with lines. So before assigning anything, I'm going to create the rest of my system. And now you'll see this is actually a very common layout for a multi-cavity tool. In this case, we'd probably have a 16 cavity tool, not just an 8 cavity. This would probably be symmetry over some sort of symmetry plane. And we would end up having a 16 cavity tool, which we'll look at in just a moment. But this is actually a very common layout, and there's 2 ways to connect these parts. There's an X layout, which basically means we're going to be going diagonally across, and then diagonally across. And then there's the H layout, which means I'm going to connect these from left to right, connect these left to right, and then connect the middle. So I'm going to do both of those situations. If you want to do that as well, you certainly can. And then ultimately, you would maybe run the simulation and see the difference between the 2. But we are actually going to analyze the difference between the 2 when we get into our simulation results. So I'm going to create more lines. So I'm going to do an H layout for the left side here. So I'm going to connect across like that. Again, I'm going to press the space bar to repeat the command. And then actually, I don't necessarily need this point here. I can actually go from using my mid snap. So down in my snap toolbar again, down at the bottom right corner, I can use my midpoint snap. to snap from the middle of this line here to the middle of this line here. And I can be confident that it actually goes straight through this point that I pre-constructed. All right, the other type of layout here is just an X, so I can just go across diagonally. You don't necessarily have to use this middle point, and I'll explain why. All right, and then I'm simply just going to go from the intersection point. I'm going to turn on my intersection snap. So I'm going to go from the intersection between these two lines to the middle. Actually, I don't need that point at all, to the middle of this runner section. All right, so these are the two commonly used types of layouts. We'll go through the advantages and disadvantages of each of these layouts when we go through the results in the next section. But those are the main types of runner layouts that are used for a multi-cavity system in most situations. Now, bringing this all the way up to the nozzle, I'm going to draw a line from the middle of this line here to this point here. And ultimately, this has to be out of plane somehow, because the sprue is always going to be in a different plane than the rest of the runner system. Or I'll say most of the time, unless you have something like a stack mold or something like that. Most of the time, your sprue is going to be kind of out of plane from the rest of your system here. So we do want to draw a line vertically, and I actually don't have a reference point here on purpose, because drawing lines vertically can be a little bit difficult sometimes. So drawing lines vertically, you'll see that if I kind of try to hover in the vertical direction, you'll see Moldex doesn't like to go in the vertical direction. It only likes to hover in the X and Y axes. And the reason for that is simply because most of your drawing is going to be in the XY plane, assuming that your parting direction is the Z axis. However, we can draw in the Z direction. It just requires an extra step. So I can go up to the top right corner of my screen. You see this little perspective tag. I'm going to double click on this, which will shift us over into a 4-pane view. And this 4-pane view will actually, if I hover over my front or my right view, I'll actually be able to create my line up in the Z direction. So it is just an extra step, but it is important to note, because there are many times where you're not just working in the XY plane, you're also working in the Z axis as well. All right, now, without any sort of point reference or any sort of point template that I gave you, you can actually customize the distance that you want this line to be. So if I want to, I can actually just type in the distance that I want this length, the length of this line. So you see this little create line thing. You see the little L equals changes as you move your cursor. But if I just type in the distance that I want this line to be, in this case 20, and press enter, you'll see that this line is, even if I move my cursor up and down, you'll see that line is locked to 20 millimeters in this case. Now, if I don't like that, I can actually just highlight that and re-enter a value. So, for example, 30. Now, you'll see that I can still move around the orientation of this line. I just can't change the length of it. So once I'm happy with the orientation, in this case, the Z axis, once I left-click, that will confirm the line and exit out of the function. So that line is now created, and we can do with it like any other line that we created earlier. To return back to my single pane or my perspective view, I can just double click on that perspective button again. And we will return back to the single view and make things a little bit easier to rotate around and view everything that we've done with this system so far. All right, so now that we've created all of the framework or the wireframe for our runner system, now we have to go in and assign everything. And the nice thing is we can do this in groups. So first of all, I'm going to assign my gates. So I'm going to select all 8 of my lines here for my gates. Conveniently enough, this will also be the first 8 lines that you created. So if you go over to your model tree, you can be confident that the first 8 lines that show up here Oops. Apparently I can't count. Oh, I'm sorry. I actually created these drops first, so it wouldn't be like that. But if you created your gates first, then it would be like that. In this case, I think it would be the first 8 every other. In this case, it seems. Either way, once you have your gates selected, then you can right-click, Edit Injection Molding Attribute. And in this case, I'm going to make these gates a hot runner gate just because they are directly dropping onto the top of the part. It's pretty rare to have that sort of situation for a cold runner. Usually a hot drop system or a hot runner system would feed to a cold runner system to get into the side of the part. But if we're directly dropping on top of the part, usually we use some sort of hot runner system. So I'm going to attribute these lines, these shorter lines, as our hot runner gates. All right, and then the dimensions here are going to be 0.5, 1.5, and 1.5. Usually for pin gates, we keep them in a 1:3:3 ratio, so the 1 being the outlet diameter or the connection between the gate and the part. So 1:3:3 ratio is typically what we use. When we're assigning hot runners, we can also assign a valve gate control ID. And I'm just going to assign a couple of these just to show you guys how sequential valve gating works in our process. Now the rest of my lines are actually going to be just hot runners. So you'll note that we assign these guys here as a hot runner gate. That gate attribution means that we are connecting our runner system to the part. That's the only place that this gate should show up. The hot runner gate attribution should only show up in the connection between our hot runner and the part. If you assign your entire runner system as a hot runner gate, you're going to run into problems in the mesher. So just make sure that only this line here, well, I guess the 8 lines, should be assigned as a hot runner gate. All right, the rest of the lines, however, are going to be assigned as hot runners. So I can either select them manually, which is kind of a tedious way to do it, or I can go through my model tree and just assign the rest of the lines that are left over. So I can take my curves, select all those. I can use the shift to select multiple or just select an entire group of objects in the model tree. And then actually, rather than right-clicking on the model itself, I can actually right-click in the model tree and attribute. Just kind of a convenient little shortcut there. And I'll attribute these all as the hot runner. Now, one thing to note when you do this is that your diameters are not going to be the same for every line here, and that's because we haven't created a connection point for certain interactions. So like this one here, we created a line all the way across, and then we created a line to the intersection between these two. There is no actual point from Moldex3D to recognize the diameter that should be available there. So it just kind of guesses, and most of the time, unfortunately, it is not correct. So for that reason, we always want to hover, or I guess in the attribution wizard here, we always want to click on the red diameter attribution and press enter, and then click on the green diameter attribution and press enter, and that will unify all of the diameters across my system. Now, if you do have different diameters, obviously you can assign those. You would just want to select them differently. Maybe if I wanted this plane to be a different diameter than the drops, then I could certainly do so pretty easily. Now, when you press the green check mark, you're going to have to give Moldex3D a few seconds. And the reason for that is because the interaction between all of the different runner segments are going to create some sort of joint connection. This joint connection will be kind of a shoring up of the volume that's left out between the connecting cylinders. So ultimately, we had a cylinder that was coming up here and a cylinder that was coming across here. Moldex3D is just connecting those two. And the cool thing is you actually have control over what this connection looks like. So if I double click on that connection or right click attribute, it's actually the same exact way as any other object in Moldex3D. I can attribute this with a different type of volume. So I can either make it a smooth, which would be like a rounded elbow, union, which would be pretty similar to what it was originally, and then two circular, which will create kind of like a more angular connection. So you have a lot of control over the different connection pieces that are created in Moldex3D. Now, one other important note, especially for a lot of you that run hot runner systems in your simulations, is that we want to make sure that when there's a valve pin, we want to remove that volume from our hot runner drops. So what I'm going to do is highlight all 8 of my hot runner drops here. You can either do that with a box select like I just did from right to left. It'll only select objects that interact with the box. You can also use shift select. Either works. And I'm going to change my cross-sectional area from circular to annular. So you'll actually see that we create a cutout of where the pin would normally go through the center of this drop. So normally these pins would be like a metal or some sort of metal. There's no reason for it to be any other material. So it would be some sort of metal going down through the middle of our hot runner, and that metal would just be pushed down to shut off our gate at a specific point in our process. So we want to make sure from a shear heating standpoint and from a cross-sectional area and pressure standpoint that our cross-sectional area is accurately defined by removing that volume that would be taken up by that metal valve pin. So the annular type cross-section allows us to do that. And when I press the green check mark, again, it'll take a few moments, but we will get a new joint type. All right, so we get this nice, cool angular joint type that we also have control over. So we can either make that the angular or slope. We can also do a flat, or we can do a round. So that is the flexibility that comes with the line-defined objects in Moldex3D. And the volume that you apply to your runner system is actually impactful to the results in the simulation. So we want to make sure to define the actual runner situation as accurately as possible. Now we're almost done. The only thing left, well, actually I guess there's 2 steps left, but they're going to be completed in one single action. First of all, you'll see that we still don't have a connection point between the different runner sections that, you know, we might have just like skipped over it by using 2 other reference points or something like that. And in Moldex, we do have to have those connection points as created. We need there to be a break in the lines whenever we go from one section to the next, or else Moldex3D doesn't really know how to mesh that. So as of right now, you can see that whenever we have a connection between 2 runner sections, we can see that there's a joint piece connected, but there is no joint piece connected, or there is no joint piece created between 2 lines where there's not a connection point. So we're going to create those connection points, and also we need some sort of melt entrance. Now the nice thing is that Moldex3D creates all of these breaks when you use the melt entrance function. So the melt entrance function is used to not only create a melt entrance, but also break all of the lines that haven't been broken up yet. And again, you do have to give it a moment. It's not going to happen instantaneously. So give it a few seconds. Don't try to rotate around too intensely, as the RAM might spike. And in some situations, if the RAM spikes, Moldex3D might crash. So you just want to make sure that that you keep everything nice and calm. Don't click too much or rotate around too much. Just let Moldex3D do what it is doing. But after you execute that melt entrance function, you'll see that those breaks have been created and all of the joint pieces have also been created as a result. The symmetry function allows us to consider the other half of our mold. In this case, we probably have another half of our mold that would be on this side. But we don't necessarily have to consider the entire second half of our mold as physical elements. We can actually create them as virtual objects using the symmetry function. So I'll just show everybody how that works real quick. If I click on the symmetry function and click on the type to be a half, and you'll see that that will just be copied over. And this section wouldn't be modeled with physical elements. We would actually be able to consider them virtually. Essentially what we're doing with this symmetry function is we're saying that whatever happens on this side of the mold is also going to happen on this side of the mold. It's just the pressure required to push the material that far into both sections is going to be doubled. So we're going to take whatever pressure is required to fill out this system, double it, and that would be the exact molding scenario as doing a 16 cavity mold instead. Once you press the green check mark, you'll see that kind of shaded or ghosted view of the symmetry function will go away. And that's just Moldex3D saying that we don't want to expect that the other 8 cavities are going to be generated. We just want or we're only going to be meshing these 8 cavities. Now, another advanced tip, especially when you're trying to do a pressure comparison between simulation and reality, is a nozzle. So the pressure drop through the nozzle is going to be extremely important to the pressure prediction through Moldex3D, and it can also impact the results that you get out of Moldex3D as well. So what is a nozzle? A nozzle is actually just an addition to the top of your sprue. In this case, I would remove my melt entrance, and then I might draw a couple of lines to represent the different sections of my nozzle. So I'm going to go back to my 4-pane view, and you can do this if you want to, or you can just follow along here. I'll do a 5 millimeter, 5 millimeter. And then one more time, I'll do a 10 millimeter. Again, this is just an extension on the top of my hot runner system. Going back to perspective view, I'm going to assign these as a hot runner. And you can make the diameter of these hot runners or the shape of these hot runners however you want. If you want to taper it, you can certainly do so. There's a lot of hot runner nozzles out there, or I'll just say nozzles in general. They're not necessarily hot runner nozzles. You can have these nozzles for a cold runner system and a hot runner system. If you're using a cold runner system, you're still going to assign these as a hot runner, and that's extremely important because the nozzle volume is always going to be filled at the beginning of your cycle. We will always have a hot runner attribution for the nozzle. So let's say I have a taper like this. And hot runner, and we'll take it out to, let's say, the green end here is going to be 2. So let's say we have a nozzle situation that looks something like that. And then I would simply just reassign my melt entrance, which should be pretty simple. So the pressure drop through this volume here is going to severely impact the pressure drop through the entire system. And when we're trying to do pressure comparisons, this is usually one of the first things we look for, especially if somebody comes back and says that there's a discrepancy between the simulation and reality. This is one of the first things that we look at is whether or not the nozzle has been modeled correctly, and ultimately whether the entire runner system has been modeled correctly. All right, so moving on to meshing. So if I go to mesh, we already went through all of the seating and parameter stuff, so you can apply that if you so desire, if you want a little bit of practice. But I'm just going to generate this straight away. You can probably see that the mesh is a little bit large on the part itself, so you could go through and adjust that if you'd like. But we'll see that the mesh actually generates exactly as it looks, with all the joint connections and all the drop diameters and stuff like that. All right, and that's basically it as far as generating a runner system in Moldex3D. There are 2 ways to do it. You can either use a CAD-defined geometry runner, or you can use a line-defined runner like we just did. So two ways to do the same thing essentially. Just the mesh type that's used is a little bit different, with the line-defined runner mesh being a little bit higher quality than the boundary layer mesh that would be created for a CAD system. And I know it can be a little bit daunting to create a wireframe layout. You can either do that in Moldex3D, you can also do that in your CAD system and bring those lines along with the part geometry, but both work exactly the same way, and you'll be able to assign those lines as hot runners, run the simulation, and be able to use solid mesh elements to run the simulation in Moldex. Now that we've gone over the setup of runner systems in Moldex3D, now it's important to go over the concepts of why we like to assign the runners in Moldex3D rather than just using something like the gates. When we're running what we call a level 1 analysis, the level 1 analysis would just be with a gate and the part. That would just be used for flow considerations and flow balance. We really want to take that all the way up to the machine to not only accurately approximate the pressure drop through the system, but also analyze things like your temperature distribution and how the melt is actually being delivered from your nozzle to the part ultimately. In an ideal world, we would be able to just have the exact same flow balance coming out of our gate as we do at our nozzle. So we would just be able to basically deliver our melt directly from our nozzle to our gate without any sort of changes. But realistically, unfortunately, because of how the polymer moves and how the polymer interacts with other polymer chains, then we aren't able to necessarily get the same distribution of temperature from our gate to what's happening at the nozzle. All right, so I want to go over two very important concepts, and that would be geometric and rheological balance. The first thing, geometric balancing, it's actually a pretty simple concept. So geometric balancing basically just means that we want the flow length to be the same between each gate or each drop in this case. So we have, in this part, we have 6 different drops. Ultimately, if I take a string and tie it to my melt entrance, I should have the same length of string through my runner system to each gate. In this case, you can actually see that that's not the case. We have a shorter flow length here and a much longer flow length here. Ultimately, what's going to happen in this case is that the melt is going to prefer to flow to one drop. In this case, it flows all the way to the end because the cross-sectional area is higher in this main drop section. A phenomenon called hesitation occurs, and we actually hesitate into the middle drops and prefer to go all the way to the end, and it causes an imbalance in our flow. We call this a fishbone type runner layout, and it's very common specifically because it's a lot easier to drill into an insert or a mold than something like a geometrically balanced runner layout, which in this case looks quite complicated, and it certainly is, but it gets the concept across that we really want the flow length to be the same between each gate. So this little squiggly here is meant to compensate for the flow length along this arm. So in this case, we actually get a nice even flow distribution because the flow length is the same from our gate to our melt entrance. Ultimately, when we run our level 1 analysis, level 1 analysis, again, is just the gates, no runner system applied. When we run our level 1 analysis, we're just kind of assuming that the melt is being delivered directly to our gates without any sort of inhibitants by the runner system. But we always want to make sure that we're maintaining that assumption by building our runner system appropriately. And the first consideration is always geometric balancing, making sure that the flow length is equal to each gate. Now we can actually lay the the flow rate graphs on top of one another, and we can see that for an uneven melt front distribution or an imbalanced runner like this, we can see that the flow rate history curves are not aligning with one another. We can see that it's kind of a jumbled up mess, no real alignment there. But once we get a nice uniform melt delivery system, then you can see these flow rate curves just kind of lay on top of one another, which is ultimately what we want to see. Now, as far as geometric balancing, there's three main strategies that are used. There's the H layout, which is the first one at the top right here. There's the X layout. These are the two that we just used in creating our runner system, or the ones that I used anyways. And there's a third one called a bracket layout. Kind of looks like a tournament bracket, and can be used to also deliver a geometrically balanced flow. Now, as far as these three systems are concerned, the X layout is usually the best as far as pressure because it has geometrically the shortest flow front. So for example, if I take the connection point between here and draw a diagonal to my part, I create a right triangle. The hypotenuse is always going to be shorter than the summation of the two right angle sides. So geometrically, the X layout is always going to have a shorter flow front, but then you start running into issues with the way that this gate is actually angled can impact your mold layout. So there are definitely considerations for using an H layout versus an X layout. And then the tournament bracket layout, I usually recommend against this just because it does have quite a long flow length with respect to the H and X, but if you are limited in space in your mold, sometimes it can be a little bit more space efficient to use a tournament bracket. You can see that you can get a little bit less space between these individual parts, whereas with the X and H, you always have to have some amount of space between them. All right, so now that we've talked about geometric balancing, now we really want to get into shear imbalance. So shear imbalance is what's actually happening on the inside of the runner. We have a nice concentric temperature distribution. You're always going to get in this case, it's a cold runner system. The hot runner system will actually be kind of similar, just except for the outside ring here. For a cold runner system, you're always going to have frozen material on the outside. And then inside of that, we're going to have a very fast gradient up to the maximum temperature. And then that will usually cool off for what's happening in the middle here. So the orange material here being a little bit cooler, just slightly cooler than the shear ring here. I'll call it the shear ring, just being the hottest material, or the red material. As we transition from the initial runner section here, this runner section is the same as this runner section. Once we transition from the first runner section to the next one, we actually get a trend of the hot material leaning towards the inside track. So when I say inside track, what I mean is the hot material will just kind of stay on the wall that it originated on. So for example, you can see here the hot material will kind of stay along this inside track. You can see it a little bit easier through the top view. You see the hot material stays here, and then the colder material then shoots out towards the outside track. And what this does is it causes a viscosity imbalance between the left and the right side of our mold, where the right side is hotter and therefore flows a little bit easier. The side is typically a little bit colder and therefore flows there's a little bit more inhibitance to the flow. So here's just an animation real quick of how that works. And then actually as we flow, we actually do get shear that's picked up along I'll say the secondary flow path, which is the cooler one. And eventually you do get warmer material that goes towards the outside track again. But the hottest material, or the lowest viscosity material, is always going to be along the inside track of our part here. And that's going to cause our imbalance in flow. Even though we have a geometrically balanced, you'll see that if you were to take a string from each of these cavities and bring them all the way up to this arrow, it would be exactly the same. However, because of the way that these parts are laid out, the temperature does not become balanced, and we actually get an imbalance. And that's something that we can see very easily in Moldex3D because we always use these 3D solid mesh elements for every object in Moldex3D. Not only the cooling system and the part, but also for the runner. we're not making any sort of approximations. We're always using these solid mesh elements to approximate exactly what's going on throughout our runner system. Now, as far as the runner systems are concerned, I've mentioned many times how geometry versus line defined, but here's just kind of a layout of the advantages and disadvantages. So for CAD, for geometry runners, they're easier to generate if your proficiency is higher in CAD. So if you have a CAD system, then it might be a little bit easier to bring in your runners as a CAD geometry. And you're able to a little bit more precisely replicate the real runner layout. Sometimes there are limitations as far as what the line-defined runners can show, or the volume that the line-defined runners can create. So sometimes you do run into that sort of limitation, but I'll say for probably 80 to 90% of the runner systems out there, Moldex3D can actually accurately define what's going on in the runner system. All right, for line-defined runners, iteration is really easy just because, first of all, we create a simple type of solid mesh with those hexa-based type elements. I say simple, they're actually very complicated, but the way we generate them is very simple. And because the generation of those line-defined solid mesh is pretty simple, means that we can iterate them pretty easily. So because the lines are behind the solid mesh, we can simply just delete the solid mesh, adjust the lines, recreate the solid mesh, and run the simulation. Rather than having to go back and forth between the CAD system and Moldex3D, you can actually just do everything inside of Moldex3D. And the other advantage of line-defined runners here being the hexa-based mesh. I'm not going to get into the disadvantages because they're pretty much just the opposite of the advantages of the opposite type. But it's always up to you whether you want to use the CAD runners or the line-defined runners. Our recommendation is always, or our best practice is always, to use a line-defined runner instead of the CAD geometry. But there are definitely advantages and disadvantages to each. All right, that being said, we're going to go through the results of a Moldex3D simulation where we actually see this sort of shear imbalance. So what I'll ask you to do is open up the folder that you downloaded called the Advanced Online Training. All right, and this this project has 3 runs. I'm going to look at, well, I guess technically it's run 4, but I'm going to look at run 4, which is called Shear Imbalance. And you'll see that I've actually created a runner system very similar to what we ended with in the first half of this discussion with runners. All right, so I have an H layout on the left side of my mold and an X layout on the right side of my mold. And we'll be able to analyze the difference between the temperature distribution in this system. So ultimately, my goal is to be able to fill out each part exactly the same, but unfortunately, we'll actually see that that's not very possible through the Moldex3D results here. So if I go to my filling results, the first thing that's going to show up is my melt front. And at a glance, you can already start to see some differences in the color distributions. But it's not really until we look at the melt front progressions when we actually get to see this sort of discrepancy. So I'm going to go over to the Result tab. So if I press my play button, actually I'm going to just take my animation slider back a little bit, and we're able to see very easily the difference between all 8 cavities here. Now this is a hot runner system, meaning that our flow is actually starting from the bottom of our gate. However, the way the melt progresses through the hot runner system to deliver the melt consistently to our part is actually going to impact the temperature distribution that we see through our runner system, and therefore the melt front progression that we get out of the runner system. So we actually do, instead of just kind of starting from a steady state condition, or I'm sorry, instead of starting from a I'll say a uniform temperature condition, we actually do run some sort of steady state analysis to make sure that we're correctly displaying or correctly calculating what's actually going on throughout the entire runner system right from the start of our flow. So you can see in this case, first of all, you'll see that almost all of the flow lengths or all of the flow progressions of the right side of our mold are ahead of the counterparts on the left side. And that is simply, again, because of the advantage of an X layout versus an H layout. The flow length is always shorter, assuming that the spacing is exactly the same. In this case, it is. The flow length is always shorter for an X layout than an H layout, which always makes it a little bit more advantageous. The pressure drop is going to be lower, and also the flow progression is going to be a little bit quicker in comparison. However, we can see really where the hottest material goes by just looking at which melt front is moving the fastest. We can see that this melt front has moved the quickest and it is filling out first, whereas this one back here is pretty much filling last. And the same is apparent over here as well. The cavity closest to the melt entrance, that's usually the trend that you'll see, the cavity closest to the melt entrance is going to fill first, and the cavity furthest away from the melt entrance is going to fill last. So that's the trend that you should always expect when you're looking at the melt front progression. But the more important thing is really to look at how the temperature is progressing through the part to kind of analyze the shear distribution. And we can actually do this really easily. I'm going to switch to my temperature result in the filling. All right, and then we actually have a couple of ways we can do this. I'm going to use the clipping tool. The slicing tool also works, but I'm going to use the clipping tool here. So the clipping tool is going to allow me to kind of slice off one half of my mold. In this case, I actually want to look at the slice of our temperature result along the parting plane. So in this case, I'm going to use the XY plane. We can see from the axes that I want to use the XY plane to go kind of across the system here. So I'm going to deactivate my YZ and I'm going to activate my XY. All right, and then to adjust this slicing plane, I'm just going to left click and drag it. So I'm going to left click drag until that slicing plane really just kind of slices through half of my runner system here. Now, obviously, I do care about what's happening in the parts, but unfortunately, the parts are skewing my scale. So you can see that a majority of the hot temperature of the material is in the hot runner, and then the colder material is down here in the part, causing our scale to skew a little bit towards the bottom. So I'm actually going to remove my parts from the display, and that will adjust my scale to be a little bit more representative of what's happening in the runner itself. You can actually see from a general standpoint, you can really see where that hot material is going, but removing the parts will make things a little bit easier for us. So I'm going to go to my model tree, and then I'm simply just going to turn off all my parts by clicking on that radio button. You can see that the scale is readjusted to give a little bit more representation of what's happening in the runner system here. So what's going to happen is the melt front is gradually going to heat up against the colder material that's right on the surface here. That moving material is going to cause some sort of friction, and it'll cause the material to heat up right along the surface here, or closer to the surface. That colder material in the middle is going to kind of shoot to the opposite side, and the hotter material is going to stay along this inner wall. And then that same progression is going to occur over here. You can see that the material actually does start to heat up as it progresses. So you can see that there is a shear heating occurring constantly. But because the top side in this case started at a hotter temperature because of this interaction over here, you can see that the temperature is a little bit hotter around this corner than it is around this corner. Now the colder material again shoots towards the outside, and we're left with two hotter sections along the right side of our runner, and the colder material kind of goes over to the left side. Now looking at the third interaction here, we can very, very obviously see how different the temperature distribution looks like between between this corner on the right side and this corner on the left side. And that is purely a consequence of the way that the melt front got to that point, or the way that the hot temperature has really kind of progressed along the inside track of this hot runner system. And we can see the same thing to the other side, except you can actually see that the difference is less intense because the starting point for the bottom side between the left and right side here than what was happening on the top side. Remember, the hottest material is always going to be along the inside track, so the hottest material is going to this drop. The second hottest material is probably going to, actually, it's probably pretty similar between this drop and this drop, just because we have the hot material kind of going around the inside track after this first interaction. But then we also have the hotter material from this first interaction going to this drop. So we actually have kind of separate interactions that will probably cause these two drops to fill out pretty similar. And then this one here is just kind of the outlier. This will actually receive the coldest material. Now the X layout is quite a bit different. So the X layout, you might actually assume that the hot material is going to prefer to go along the easiest path, which would be along the right side in this case. But actually, the same progression occurs for the X layout than it is for the H layout. So the material will prefer to just stay along this inside track. You can see there's a little bit of a disturbance here, and this is actually a real phenomenon that you'd see. But you can see that the hot material does prefer to stay along the inside track in the X layout, just like it does for the H layout, which will cause this part to fill first. And I would assume that these two might be similar, and then this one again would be the last one. So the general trend of the flow, or the general trend of the imbalance, will be the same between the H and X layout typically. It's just the consideration of which one is more efficient, which one is more possible for your mold layout is the one that you'll want to use. All right, so you can also adjust your scale a little bit to make this, or I guess to intensify this variation in temperature. So you can see that there's a very low amount of the dark blue material. So I can actually take this scale up a little bit. And we really get to see a better, it kind of removes a lot of what's happening right at the right in the main sprue here. You actually see that the material is heating up quite a bit, or the temperature is increasing quite a bit over the flow length. But you can get a better idea of where that high temperature is located by diversifying the temperature, or I guess the color gradient in your result here. So just another way to view it. But this shear heating problem is going to be apparent whether you use the line-defined or a geometry system. Both should be able to pick this phenomenon up. But the most important thing is that we're using the 3D solid mesh elements to calculate what's actually going on, rather than just kind of creating some like junction assumptions, or just assuming that the melt flow creates some sort of pressure drop. We actually want to see what's actually happening with a 3D solid mesh. Thank you for watching this Moldex3D advanced tips and tricks, and go beyond simulation with Moldex3D.